Okay, so hi. So it is our part 2 of our lecture, geometry, vector and the gravity. And in the last class I have just introduced to you all of the geometrical mumbo jumbo. So it is there actually. So if it is a circle of radius r, and if I inscribed n-sided polygon here, and the values of each of the sides is v, then okay, so it is actually the angle is a 360 degree by n, because it is a n-sided polygon. Okay, and so I just got a results. The Bn is the Bn actually, the v squared by r, right? V means the sides of the polygon, I mean the length of the sides, the regular polygon. So it is AB is a V, then obviously the BC is a V, CD is equals to V, DE will be equals to V, right? Because it's a regular polygon, right? Okay, and the radius of this circle is a R. Okay, so the Bn is actually V squared by R. Okay, so these I just got from our previous lecture. Now I will introduce to you uh, just a very simple thing, subtraction of two vectors. Okay, I had introduced the subtraction for part 3 of our vector series, right? Subtraction of vector. So if it is just think it is a v1 and the vector v1, and if it is a v2, then obviously this thing will goes v2 minus v1, right? Subtraction of v2 from v1, it is actually this thing. Yes, I introduced previously from our lecture series of vector, I mean vectors for dumb, right? Part 3, right? The subtraction rule of vectors. If it is a v1 and it is a v2, then obviously this line and these arrows will goes to v2 minus v1, right? Okay, so now I will introduce to you uniform circular motion, right? All of you know, hopefully all of you know from your class 9, 10 sense, uniform circular motion, right? Okay, so just erase this part, v2 minus v1. Just remember, if it is a v1 and it is a v2, then these arrows actually goes to v2 minus v1, right? Okay. Okay, so it is a uniform circular motion, I mean UCM, the uniform circular motion. Okay, so first of all, the circular motion means if an object or if a particle just trace down a circular path, it is a circular motion, right? If an object or a particle trace down a circular path, then the path, I mean the motion of the particle or an object is called a circular motion. Okay. Okay. So if it is the center of the circle, if an object goes in the circular path, I mean if it is traced down a circular path, then the motion of this particle or this object is actually circular motion, right? Okay. And what is uniform circular motion? Uniform circular motion means if each and every point of this path, right, each and every point of this path the particle goes with the same speed, right? Each and every point of this path, I mean the circular path, the particle goes in the particle traced the same speed. Okay. So it is called a uniform circular motion. The circular motion means if an object or a particle traces down a circular path, then it is called a circular motion. And the uniform circular motion means if the particle, each and every point of this line, I mean each and every point of this path, if the particle has the same speed, right? So it is called the uniform circular motion. Okay. Okay. So just take it. It is an origin. I mean, sorry, the center of this circle O, and let's, if the time t, the particle is here. T equals to 0 is here, and some t equals to 1 second is here, and t equals to 2 second is here, right? And so many. The t equals to 3 second here, t equals to 4 second here, t equals to 5 second here. I mean t just time. Just take it. If the time just start here. Particle is here, t equals to 0, and after the 1 second particle is here, and after the 2 second particle is here, after the 3 second particle is here, right? And what is the velocity? The velocity actually, if you draw a tangent from this point, it is called a velocity of the particle, right? So it is a velocity. Let's take the particle moves in the counterclockwise direction. In this direction, counterclockwise direction, the velocity of this point is actually in that direction. Okay? And all of you know the magnitude of velocity. Magnitude of velocity is the speed, right? The magnitude of velocity means just speed. Okay? Okay. The magnitude of velocity means the speed. I mean the magnitude of this arrow is same because it is the uniform circular motion. I mean the speed will be the same, right? That means the length of this arrow, I mean the length of this straight line will be same. So if at this point the velocity is that direction, so obviously at this point the velocity is this, right? Okay. This is very simple case because the length of this straight line will be same because the speed, length of this straight line means the speed, because the magnitude of velocity means speed, and for our uniform circular motion, the speed will be same. So obviously the speed, I mean the length of this straight line will be same, right? Okay, so just take it initial velocity v1 and the final velocity v2, right? So I want to calculate the change of velocity, right? The change of velocity. So what will be this thing? Just all of you know from our vector for term classes, right? Just translate v2 from here to there. Just a parallel transformation. It is a new v2 actually. And from our previous calculations, I mean the previous source, it is a v2 minus v1 means this thing actually. v2 minus v1, right? And all of you know what is v2 minus v1, the change of velocity, right? And the final velocity minus initial velocity, that means change of velocity, right? And it is actually change of velocity in 1 second. is that t equals to 0, is that t equals to 1. So all of you know the change of velocity per unit time, it's called an acceleration, right? So it is actually acceleration. The direction of acceleration is here, and it is actually directed towards the center. Okay, so it is called a centripetal acceleration. Okay, centripetal means directed towards the center. Okay, so it is a centripetal acceleration is here, and the change of velocity per unit time, right? Because in time t equals to 0, the particle is here, and the time t equals to 1 second, the particle is here. And just I translate this final velocity from here to there and just subtract this thing, v2 minus v1 here. And all of you know the acceleration means the change of velocity, that means final minus initial velocity is called acceleration per unit time, and it is a unit time, right? Because it is a 1 second. So it is a centripetal acceleration, I mean towards the center, right? And now I want to calculate the magnitude of this thing. Okay, just the magnitude of this thing. Okay, the magnitude of this thing, what will happen is the magnitude of this thing. And just obviously the length of this straight line, I mean the magnitude of velocity, will be same because it's a uniform circular motion. That means magnitude of velocity means speed. The speed will be same, right? That means this straight line actually is magnitude of this straight line and this straight line are same. Okay. Okay. So what will be this I mean the magnitude of direction, just I want to calculate, right? The magnitude of this acceleration. Okay. Okay, so just erase something from here, and okay, and just I draw here a circle obviously, and a circle with a radius r, I mean the particle traced down the circle of radius r with a speed v, right? Particle traced down the circular path of radius r, and the speed is v, right? Okay, so I just inscribed here a n-sided polygon, right? A n-sided polygon. Just I inscribed here the n-sided polygon. Okay, just these are 3 or 4 sides I just draw. Okay, and of course when the particle is here, then t equals to 0, obviously the velocity of the particle, I mean this thing, right? Okay, just named it O, A, B, C, D, E. Okay, and when the particle is here, just take it is a magnitude of velocity, I mean the speed, and I just inscribed here the n-sided polygon with the sides v, right? I mean it is a v, it is also a v, it is also a v, it is also a v, and it is also a v. Okay. Okay, and I just named it somehow P. Okay, in this point. Okay, and then after 1 second, t equals to 1 here, the particle traced down from here to there, and obviously the velocity is that direction. Okay, because the same speed, right? I mean the magnitude of this thing will be same. Right? Just look at this stuff here. This thing actually, this, the same, just the same, just a parallel transformation. It is actually it is, and these actually these. Okay. So if I erase this velocity and I take this thing with an arrow, so it is our velocity, right? Okay. Okay. And now just translate this thing AB from here to there. I just erase it. Oh, just here to there. So if it is a V, obviously it is a V. I mean the length of this thing is same. And I just want to calculate the acceleration, I mean this thing. Okay. Just think this is actually towards the center, the centripetal acceleration, and if it is V and if it is a V, then from our previous picture, it's the Bn, right? The acceleration is here, the Bn. Yeah, it is somehow Am, just write it Am. Okay, so it is the Am and the Bn, the same thing, right? So it is obviously a V square by R, right? So it is our centripetal acceleration, I mean the magnitude of centripetal acceleration, the V squared by R. Okay, so if the particle with speed V traced a circular path with radius R, then the centripetal acceleration goes to the magnitude of centripetal acceleration, which goes to just a V squared by R. It's a magnitude of your centripetal acceleration, right? Centripetal acceleration. It is a very interesting result. It is actually the magnitude of centripetal acceleration, right? Okay, just same thing here, there, just the same thing. I just calculated previous lecture, and from here I just, from the uniform circular motion, it is the length of our acceleration vector. I mean the magnitude of centripetal acceleration is just V squared by R, right? And just think, the radius of this circle is a constant. The all of them, it is a R obviously, it is an R obviously, it is an R obviously. So radius of this circle is constant, and the particle will goes the same speed, right? I mean V, just same speed. That means V. So V and R is the same for each and every points in that circle, right? So obviously, if it is the acceleration, it is a V squared by R. I mean the magnitude of acceleration is a V squared by R. So if the V is constant for the uniform circular case, and then radius is obviously the same, right? Because in a circle, the radius is constant. Then acceleration should be constant, right? The acceleration is constant here, right? Okay. Acceleration is constant. Now, just place this particle or an object with our planet, right? Just take, instead of our particle or an object with a planet, it is somehow a planet. It is somehow a planet which travels in a circular orbit, and to the center here there is the sun, right? It is the sun. Just place, instead of an object or a particle, it is a planet, just revolves in a circular orbit, and with the center is the sun, right? Okay. 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 Now this thing is a planet moves in a circular orbit with radius r with a constant speed v. Okay, constant speed v. It is actually a simplification of elliptical orbit, but it is probably sufficient, right? This thing and planet moves in a circular orbit around the sun, right? Okay. And just take t equals to 0. When the t equals to 0, the time t equals to 0 seconds, and the planet is here, and after t equals to 1 second, the planet is here, right? And after t equals to 2 seconds, the planet is here. After t equals to 3 seconds, the planet is here. So it is a t equals to 2 seconds and the t equals to 3 seconds, right? Okay. So just I want to calculate the area traced down by the planet, the area traced down by the planet, right? And when the planet is here and just goes from here to there, the area traced down with the sun, it is this thing, right? And after 1 second, from here to there, the planet goes from here to there and area traced down this thing, just a dotted region here. It is a slashed region here, it is a dotted region here. And just obviously it is r, so it is also r, the radius of the circle, it is also r, the radius of the circle. And obviously if it is v, then obviously it will be a v. So it is an isosceles triangle with the two sides are equal to r and third side is v, and obviously it is an isosceles triangle, the two sides equal to r and the third side is v, right? So obviously the area, just take it O and just name it B. So obviously the area of triangle OAP equal to the area of triangle OAB, right? Because these two are same. It is R, it is R, it is V, and obviously it is R, it is R, it is a V. So the area of these two triangles are same. So it is our Kepler's second law, right? It is a Kepler second law. That means the planet traces down equal area when the planet swipes equal area in equal time, right? Just it is a 1 second. Yeah, it is a 1 second. The planet swipes the area of this thing slashed region. In 1 second, the planet just traveled from here to there. The area swipes out this thing, and just after 1 second, from t equals to 1 to t equals to 2, the planet swipes equal area, right? This is equal time, t equals to 0 to t equals to 1, that means 1 second, and t equals to 1 to t equals to 2, that means another 1 second. I mean for each and every second, I mean each and every equal time, the planet swipes out equal area, right? So it is our Kepler second law of gravity. The planet swipes down the equal area and the equal time, right? This is our Kepler second law, right? Number 2 laws of Kepler, the planet swipes out equal area in equal time, right? It is here. Just the planet swipes out equal area in equal time. Just take it is a 2 area and just take it from the planet goes B from B to C, and then the area traced out this crossed region, right? Just a crossed region, and just think it is obviously R. So it is R, and obviously it is a V, right? Because it is our regular polygon. I mean, the speed of the planet is the same, right? It is V, it is V, it is V. So obviously this area will equals to this area will equals to this area, and obviously it is in 1 second, from t equals to 2, from t equals to 3, right? The planet swipes out equal radian equal time. These are very interesting results for our Kepler's geometry, Kepler's law of gravity, right? Okay. Now, by some observations from Ptolemy to Galileo to Copernicus to the Tycho Brahe. Okay, the Kepler formulated his third law actually. His third law was actually the t square proportional to r cube. It is actually by observation, right? I would not want to show this thing actually. It is actually by observations. The Kepler suggests, the Kepler formulated these laws by just last 400 for more, just 1,000 years observation. From the 1,000 years observation before the Kepler formulated this law was t square proportional to r cube, right? What is t? T means if the planet goes from here and then come back to the here, the time period of planet, just a time period of planet, when the planet is here and just travels down this circular path and come back from this position, the initial position, it is called the time period, right? The time taken by a planet to come back to its initial position, it is called a t, right? Time period. T means the time period. Time period means, all of you know, when an object travels down some path and just come back the same position, the initial position, the time taken by this object is called a time period, right? If the planet takes the time to reach the same initial position after travels circular path, so it is a time period, right? So it is a t. It is a t, and r means the radius and the distance from the sun, right? The distance from the sun to the planet is r here. Is r. T means time period. The time period means the time taken by a planet to trace down from initial point to the same initial point, right? From here, it trace down some path and goes to same initial point. This is the time period of planet, and the radius is actually the distance from the sun to the planet. It is the third law of Kepler, but it is actually the observational law, right? Because 1,000 years observation, and then the Kepler decides to formulate these laws, right? T square proportional to r cube. It is actually the masterpiece. T square proportional to r cube is a very beautiful laws actually. The Kepler third law, right? Third law of Kepler. Okay. So erase this thing is happening here. Just geometrical configuration. Erase this thing, and from the constant acceleration, that means A equals to v squared by r. R means the radius of this circle. Okay, just take it smaller, right? Because for our similarity of our picture, just take it smaller. Okay, just don't think it is actually our observation, by our observation, the 1,000 years astronomical data. Okay, from the 1,000 years of astronomical data, Kepler suggests this laws, right? The t square proportional to r cube. T means the time period of the planet, and r means the distance from the sun, right? Okay. Okay, and I just show here this acceleration is constant, right? Because v is constant throughout the path, and r obviously constant. So it is a constant. It is a constant. Okay. Okay. And if the particle travels from here to here, I mean the same position with time t, right? I mean the time period. If the particle goes with one time period, I mean the particle travels with one time period, the particle reaches actually the same position, I mean the initial position. Okay. The length of this path actually, all of you know, the perimeter of this circle, the 2 pi r. Okay. So all of you know actually, the time period t means the length, time means the distance by velocity. All of you know from your class 8, 9, 6. Time means the distance by velocity of an object. Right? Here is a planet. Okay, and the distance traveled by a planet with one time period, and when the planet is here, it's t equals to 2, t equals to 0, and after the capital T, the planet will reach the same position, I mean the one time period. S is actually the perimeter of this circle. That means if the radius is r, then the perimeter is actually 2 pi r by v. Okay. So it is the v actually here is a t, right? T means 2 pi r by v. So v means just a simple 2 pi r by t. Just very simple thing. And the v square means just 4 pi square r square by t square, right? And just place it, the v square here. So the 4 pi square r square, 4 pi square r square by t square, and down here the denominator, that is r, is a constant, right? Then cancels 1r with 1r. Then the results when it goes 4 pi square r by t square. It is actually acceleration, right? It is actually an acceleration. Okay. So it is acceleration here. Okay. So now just place t square proportional to r cube from here to there. I mean the Kepler observations, and the Newton counts here. Okay, so Newton counts here. R and r cube cancel out. The result will go 4 pi square by r square, right? So the acceleration basically proportional to 1 by r square. Somehow 1 by r square, right? And if the mass of the planet is m, I mean the small m, it is actually the acceleration of planet, right? And if the mass of the planet is m, then the force on the planet is actually mass into acceleration. All of you know the mass into acceleration. The force on the planet goes to m by r square, right? M by r square. The Newton deduced his laws of gravity here. M by r square, right? And from his third law of Newton, if the planet, if the sun, actually here the force actually, the force F, here the force actually acts on the planet by the sun, right? Is a mass, just take it the mass capital M, the sun. Is the force on the planet by the sun, right? Because the sun is in the center. And obviously from our third law of Newton, the action reaction pair. So if the force on the planet is here, then is a mass of this planet, then obviously it is equal, just equal and opposite the force on the sun, right? See, the force on the planet is the force on the sun is actually equals to just a proportional. I mean, here the force, the force on the planet is actually proportional to its mass. And obviously all of you know the force on the planet here is actually equal and opposite the force on the sun. So the force on the sun will be proportional to mass of the sun, a capital M, right? And if you just combine these results, okay, Fp equals to m by r square, or Fp proportional to m, and these two forces are equal, right? Fp and Fs. The force on the planet, the force on the sun should be equal because the action reaction pair. So obviously the force is actually some constant g. Just name g constant. Is the m and the m by r square, right? M by r square. It is the gravitational laws given by Newton, right? Okay, and okay, so it is the all of this lecture, geometry, vector, and gravity. And in the next class, I will just turn back to our vector series, the vector for term. Okay, okay. Just please like, share, and comment, and obviously subscribe. Okay. Okay. So it is a very simple thing. Just a very simple thing. The masterpiece there, t square proportional to r cube, right? It has the masterpiece. And then obviously all of the redundant here. If p goes to m by r square, when acceleration proportional to r square, force obviously mass into acceleration goes to here, and p proportional to mass obviously, and then the force on the planet is exactly equal and opposite on the force the sun. So Fs, the force on the sun proportional to the mass of the sun. Just combine this result. F equals to gm by r square. G is a constant, right? Because the proportionality constant. Okay. Okay.